Welcome to This Explainer. Listen, today we are embarking on a high-stakes mission briefing. Our operational theater, the Cambridge Mathematics Examinations. And it doesn't matter if you're navigating the 0580, the Additional Mathematics 0606, the 4024, the 4037, or the 4040. The physics of this flight remain exactly the same. Our specific launch coordinates for today's operation, the remainder and factor theorems. I want you to treat this explainer exactly like a mission control sequence. Because in that Cambridge exam room, there is absolutely zero margin for error, none. Every single calculation, every logical step, every substitution must be perfectly, flawlessly calibrated for launch. To really illustrate what's at stake here, I want you to picture a dynamic split screen right now, showing two candidates we see all too often in the principal examiner reports. We'll call them Alex and Sam. Now, Alex is brilliant at memorization. He literally overloads his paper with raw mathematical facts, writing down every single thing he knows about polynomials. But he provides zero structured analysis. He just dumps numbers onto the page and hopes for the best. On the other side of our screen, we have Sam. Sam actually understands the math perfectly, but he rushes the launch sequence. He completely misses the specific command word requirements in the prompt. When we look at their past paper answers side by side, it is just a sea of red pen marks. And here's the tragedy. They are bleeding marks not because they don't know the math, but because their flight trajectory is entirely uncalibrated. This explainer is going to transform those red marks into green check marks. Let's get our launch sequence started.
Okay, let's do a quick rundown of our mission flight checklist. First up, a mission brief on core concepts. Second, we'll crack into the method mark strategy. Third, we establish our standardized processing sequence. Fourth, we are navigating examiner traps. And finally, our mission evaluation.
So, let's initiate Phase 1, Mission Brief, Core Concepts.
To secure a successful launch, we really need to look under the hood at the core principles of the syllabus. What are the examiners actually looking for when they mark your paper? It's not just about finding the magical value of x or the remainder r. They are targeting very specific cognitive domains. As the slide brilliantly illustrates, Cambridge is hunting for three distinct assessment objectives: knowledge and understanding, application, and analysis. Think back to our student Alex for a second. Alex has that first domain absolutely locked down. He has the knowledge. He knows all the formulas. But he completely fails at analysis. Mastering these domains requires a connected, deeply conceptual understanding. You must be able to successfully transfer your knowledge of, say, the remainder theorem to completely unfamiliar contexts. This is where we apply a highly specialized framework. I want you to think of it like the Peel framework that's often used in English or history essay writing, but we are adapting it for pure mathematical logic. Peel stands for point, evidence, explanation, link. What is the mathematical point or principle you are using? What is the evidence or execution of your working out? What is the logical explanation of your successive steps? And how does your final answer link back to the original command word in the prompt? If you structure your mathematical arguments this way, you're going to hit every single assessment objective flawlessly. And hey, before we continue, subscribe to our YouTube channel Ace the Exams at acexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Trust me, calibrating your approach with these frameworks is the ultimate game changer.
Now, what's really fascinating about this next slide is the stark contrast between analytical depth and superficial breadth. You see, Cambridge academic benchmarks strictly demand deep, logical, structured reasoning over shallow, rapid-fire memorization. Remember our other student, Sam, the one who rushes everything? Sam exhibits superficial breadth. He tries to quickly do a bit of polynomial long division over here, maybe a really quick messy substitution over there, but he completely lacks the analytical depth to prove why x minus a is actually a factor. He's just skimming the surface of the problem. To capture those absolute top-tier marks, we have to move past simply listing equations and actually construct airtight mathematical arguments. You have to prove to the examiner, beyond a shadow of a doubt, that you understand the mechanics of the theorem, not just the final destination.
Moving right along to Phase 2, the method mark strategy. Let's go back to our space mission analogy. If the final, correct answer is your rocket landing perfectly on the surface of Mars, the method marks are the vital telemetry data being constantly beamed back to Earth during the entire flight. Even if the final landing is slightly bumpy, maybe you dropped a negative sign at the very last microsecond of the calculation, the method marks ensure the overall mission isn't a total failure. You still get the vast majority of the credit. Take a look at this quote. We source this directly from the Examiner Foundations. Presentation of information follows strict conventions: proper headings, correct terminology, appropriate formats, and clear annotation. So the absolute crucial takeaway here is that presentation isn't just about making your paper look pretty or aesthetic. It is a strict, non-negotiable convention required to secure those vital method marks. If you just scribble numbers haphazardly in the margins, the examiner cannot track your telemetry. They literally cannot award you method marks for your logical process because they don't know what you were trying to do. Imagine taking a messy polynomial long division, actually aligning the powers of x properly in columns, clearly stating let f of x equal before you begin, and clearly annotating your final remainder. That is exactly how you visually guide the examiner through your mathematical logic. You are essentially holding their hand and saying, look at my perfect flight path.
All right, phase 3, the standardized processing sequence.
Listen closely because you shouldn't be making up a brand new way to solve a remainder theorem question every single time you sit down at a desk. That is a recipe for disaster. You need a reliable, highly engineered 5-step launch sequence that you can deploy on autopilot. Here is the exact framework you need to internalize. Step 1, identify key elements. Are they giving you a factor or are they giving you a remainder? Read the prompt carefully. Step 2, apply relevant principles. If the prompt says it's a factor, you instantly know the mathematical principle is f of a equals 0. Step 3, execute analysis with clear working. This right here is the engine room. This is where your algebra must be absolutely flawless. Step 4, verify results. Does the value actually make sense in the context of the problem? Step 5, present an appropriate format. Let's do a quick mental exercise to lock this in. Imagine you get a past paper question that reads, find the value of a when the polynomial 2x cubed plus ax squared minus x plus 4 leaves a remainder of 10 when divided by x minus 2. Okay, let's run the sequence. Step 1, the key element is a remainder of 10 and the divisor is x minus 2. Step 2, the principal is f of 2 equals 10. Step 3, we execute the substitution. You write it out. 2 times 2 cubed plus a times 2 squared minus 2 plus 4 equals 10. You do the algebra beautifully. 2 cubed is 8 times 2 is 16. So 16 plus 4a minus 2 plus 4 equals 10. Simplify it. 18 plus 4a equals 10. Move the 18 over. 4a equals negative 8. Step 4 and 5, you write a equals negative 2 and you verify that an integer makes sense here. Executing this specific analysis with clear step-by-step notation ensures absolute precision every single time.
We are now entering phase 4, navigating examiner traps. Pay close attention.
Deep space is full of hidden hazards, and the exam paper is no different. These are the black holes that derail thousands of candidates every single year. And we know exactly what they are because we have the ultimate intelligence briefing, the principal examiner reports. We read them so you don't have to. Here are the top 3 mission-critical mistakes students make. First up, using the wrong approach for the wrong context. A question might specifically say, using the remainder theorem, find, but a student decides to ignore that command and do full polynomial long division instead. Is it mathematically sound? Yes. Will it get the right answer? Probably. But it's the wrong approach for the specific context demanded by the command word, and it wastes precious time. Second trap, forgetting to check format and presentation. This goes back to losing that vital telemetry data we just talked about. Third trap, providing answers not specific to the context given. Let's do a quick Find the Flaw interactive challenge right now. I want you to imagine a student does all the brilliant algebra in the world and figures out that x equals 2 and x equals negative 3. They proudly double underline these answers and move on to the next page. But wait, the prompt explicitly asked for the coordinates of the points of intersection on a curve. Do you see the flaw? I'm giving you a few seconds to spot it. They didn't provide the y values. Boom. Context missed. Marks lost. They did all the hard work and threw the points away at the finish line. Stop scrolling. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to @acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. Seriously, avoiding these specific traps is how you secure those grade boundaries.
And that Find the Flaw exercise leads us perfectly into a massive flashing red alert on the examiner reports. We call it terminology confusion. Time and time again, candidates completely fail to define key terms before using them in their extended mathematical responses. Look, if you are going to substitute a value into an algebraic expression, you cannot just start writing random strings of numbers equal to 0. You must define the terminology for the examiner. You literally just write let f of x equal and then write out the full polynomial. Only then do you write f of a equals 0. By explicitly defining your terms right at the start, you are signaling to the examiner that you are in complete, masterful command of the mathematical language.
You aren't just guessing, you are speaking their language.
So, pivoting from avoiding mistakes to actively synthesizing information, we really have to ask ourselves this critical question. How do we draw evidence-based conclusions from complex data? I want to run a quick data scan challenge with you. Imagine I put a massive data table on the screen right now, showing a cubic function's values for various x inputs. You've got a 60-second timer ticking down in your head. You scan the table, you see x equals 1, y equals 4. You see x equals 2, y equals 0. You see x equals 3, y equals -5. Time's up. What is your mission? Your mission is to extract the core mathematical trend immediately. The evidence-based conclusion here? Because y is 0 exactly when x is 2, then by the factor theorem, x minus 2 absolutely must be a factor of that cubic function. Bam! You just extracted the hidden relationship and drew a massive mathematical conclusion directly from raw tabular data. That is exactly the kind of rapid, precise analysis required to ace these papers.
We have reached Phase 5, the final mission evaluation.
Pay attention, because this slide is where we separate the A grades from the A-star grades. This is the ultimate problem-solving pipeline used to completely master the highest-order assessment objectives Cambridge can throw at you. Tier 1 is deconstruct. What is the question actually telling me beneath the surface? Identify every single piece of given information. Tier 2 is solve. Break the massive problem into small logical steps and process it systematically using the Peel framework and the 5-step sequence we just established. Tier 3 is evaluate. You must check for reasonableness. Let me give you an example. If you calculate the length of a side of a triangle using a complex algebraic equation and your final answer is a negative number, you must evaluate that. You have to realize, wait, a physical length cannot be negative and explicitly state that you are rejecting the negative root. You must justify your final state. I challenge you to a speedwriting exercise when this session is over. Give yourself 30 seconds to write one perfect paragraph applying these 3 tiers to the last tricky math question you got wrong. It will change the way you think.
Now, part of that higher-order Tier 3 evaluation often involves comparative analysis. When a question prompts you to evaluate different mathematical approaches or analyze 2 distinct algebraic structures, true comparative analysis requires identifying both similarities and differences. You must use comparative connectives and solid mathematical evidence. You can't just vaguely assert, well, this method is better, or this polynomial is bigger. You must prove it logically through your rigorous working out. Show the examiner exactly why one approach yields a remainder and the other yields 0.
Before we wrap up, I want to give you a secret weapon. The Cambridge syllabus involves highly abstract math, and under exam pressure, it's easy to blank. To secure these concepts permanently in your mind, I want to share a visual story method. You need to encode the remainder and factor theorem concepts into a physical, real-world journey. Picture a massive industrial machine, a factory. The long, complicated polynomial is the raw material going into the machine. The divisor, let's say x minus a, is the specific cutting tool. If the cutting tool is perfectly sized for the material, meaning it is a mathematical factor, it slices cleanly. There are no scraps left on the factory floor. The remainder is exactly 0. But if the cutting tool is the wrong size, it hacks away, and there are random scraps left over. Those scraps, that's your remainder, R. By anchoring highly abstract math to vivid visual stories like this, you ensure the core concepts are instantly retrievable, even when the exam hall clock is ticking down and the pressure is at maximum.
And so we arrive at our final, provocative question of the briefing. I want you to go look at your past papers right after this. Look closely at your working out. Will your current methodology actually survive the intense scrutiny of a zero margin for error Cambridge launch? Or are you leaving your telemetry data, those precious life-saving method marks, scattered and lost in deep space? It's time to find out. And listen, students who implement these exact mathematics strategies see an average improvement of 2 full-grade boundaries. But that only happens if they practice consistently with our weekly explainer videos. So here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at Ace the Exams IGCS to excel in your Cambridge examinations. Subscribe right now to @Ace the Exams IGCS and click that bell. Don't let another exam pass you by. Finally, I want to hear from you. Drop a comment below with your target grade for mathematics and the single biggest challenge you're facing right now. Our team responds to every single comment. Like and share this video with a study partner who needs to hear this. Ace the Exams, your Cambridge success starts here. See you on the next mission.